Hello everybody, today we're going to talk about derivatives of inverse functions, but before we get there are a few reminders that we should have about inverse functions that will be important to us. One of the first things to recall about a function having an inverse is that a function only has an inverse if it is 1 to 1. In the case of my example on the page here, y equals x cubed plus 1, if we let the function f of x, there it goes, equal x cubed plus 1, we do have, in fact, a 1-to-1 function. We know that it's 1-to-1. If we were to look at its graph, it would pass the horizontal line test. But even more than that, we know that if there are any two values of x equals a, x equals b, where a does not equal b, that f of a only equals f of b if and only if a is equal to b. Right? So if a does not equal b, we knew that a cubed plus 1 will certainly not equal b cubed plus 1 for any two separate values. Right? So we know that that's got to be a 1-to-1 function. All right, so f of x equals x cubed plus 1 is a 1-to-1 function. For any function f and its inverse, which we use the designation f inverse with a little -1 superscript up there, f inverse of x, which is in this case the cube root of x minus 1, if we were to take the composition of these two functions, we know that the result of that composition will be x. We can verify that by using this composition here, f of f inverse of x, which would be equal to the cube root of the quantity x minus 1 raised to the third power plus 1, which becomes, well, x minus 1 plus 1. Yeah, we just get x. And it would work the other way around as well. Okay? The domain and range of a function f is the range and domain respectively of the inverse. And we can see that in the case of this limited domain function that I've made up, where the domain goes from 0 to infinity, that becomes the range of our inverse function 0 to infinity, and the range of the original function y greater than or equal to 1 becomes the domain of our inverse. Finally, the graphs of the function and the inverse mirror each other about the line y equals x. And if we take a look at the line y equals x, we know this is true because in this mirror image, if on our original function we have the point 2, 9, because 2 cubed plus 1 is 9, then we're going to end up on the inverse function with the point 9, 2, which again makes sense because if we take 9, subtract 1, and get its cube root, we definitely get 2. Realizing these things about our inverse functions, we have two other properties that we should state. The first property is that if f is a function whose domain is an interval, here's our interval, 0 to infinity, and if f has an inverse function, then the following statements are true. First of all, if f is a continuous function on its domain, then f inverse must also be continuous on its domain. So if we look at the graphs of f and f inverse over their respective domains, we do indeed find that these functions are continuous. Not only that, but if f is differentiable on an interval containing some value c, and f prime of c is not equal to 0, then f inverse is also differentiable at x equals c. And just to see that, let's pick a point like x equals 2. We know that this graph is continuous at the point 2, 9. We go through our three conditions for continuity, limit definition of continuity, and work that out. But in this case, what else could we say? Well, in this case, if we were to find f prime of x, y prime in this case is equal to 3x squared, we would find that y prime, when evaluated at x equals 2, is going to give us 3 times 2 squared, which is to say a slope of 12. It is indeed the case that as long as f prime is not equal to 0, then f inverse is equal to f of c. Well, what is f of c? If we're letting c equal to f of 2 is equal to 9, and therefore f inverse of x will also be differentiable at the point x equals 9. Get it? At x equals f prime f inverse at f of c. F of c is 9. There we go. Okay. So if we work that out, we would, of course, find that our inverse function, if we take y prime there, we would get 1 over 3 times the cube root of x minus 1 quantity squared. And you can work that out for yourself. And of course, we would certainly find that y prime does exist at 9 by making the substitution into our function and finding that y prime would be equal to, hello, my pen, y prime would be equal to 1 over 3 times the cube root of 9 minus 1 squared. Well, the cube root of 9 minus 1 squared is the same thing as 2 cubed, 2 squared, which we found was equal to 12, so we would get 1/12 as our slope in that case.